Hi guys, as we get real close to the end of the course here, we want to take a little bit of time and look at some of the mathematical aspects of hydraulics. Let's take a look at some math that we can do involving hydraulic pumps and hydraulic cylinders. So for starters, hydraulic pumps. If you ever look at a hydraulic pump, it's always rated in two ways. It's rated according to its flow rate, which you've probably seen. That's how many gallons per minute of fluid it can pump under pressure. So that's always rated in GPM, or gallons per minute. And of course, as you can probably guess, that flow rate is determined how fast the cylinder or the hydraulic motor that it's operating is going to operate. So in general, the higher the GPM, the faster your cylinder or motor will move. No surprise there. So we can calculate the flow rate in gallons per minute. So here it is. Here's a formula for your gold sheet or your conversion sheet. In general, the flow rate of a pump is very easy to find. You just need the displacement of the pump. That needs to be, by the way, in cubic inches. And we find that the same way that we find engine displacement. Multiply it by the number of RPM, and then divide by 231, since there's 231 cubic inches in a gallon, and we're trying to get this thing into gallons per minute. So I'm going to quick pull up a little video here. So I just want you to take a look at inside of a typical piston pump. Of course, you've got a swash plate over here that's turning and drawing each of the pistons down in their bore. They pull hydraulic fluid in on the intake side. There's two big ports on either side. One side is allowing fluid to be pulled in. The other side is allowing it to be squeezed out. The angle of that swash plate is determined what your flow is. Sometimes you can't control the engine RPM. So by putting that gray swash plate at a steep angle, the pistons go way down in their bores, pull in a lot of fluid. If you don't need flow, but the engine's got to keep running, you can straighten out that swash plate, make it more vertical, and you can see the pistons don't go so far down in their bores. And in fact, you can completely stop flow if you make the swash plate go completely perpendicular to the pistons. Then it'll just sit and spin. But we angle that swash plate, fluid flow starts again. So we're going to work with the bore and stroke of each of these pistons, and that's no different than the pistons that you would see inside the cylinder of an engine, except they're a whole lot smaller. Okay, so getting back to business here, flow rate is the displacement in cubic inches times the RPM divided by 231. Let's take a look at an example. Here's a nice simple case. The pump below has these pistons in here, and it doesn't say how many, but we can count them. There's number 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a 9-cylinder hydraulic pump. It's got bores that are 0.85. Of course, they need to be fairly small. We get that high heel effect, as we saw in the last lesson, so we get the real high pressure by using small pistons. And a 1.5-inch stroke. And that's assumed with the swash plate fully extended, so that's maximum flow. What's the flow rating at 2400 RPM? Well, here we go. Let's find our displacement. The displacement, since we're dealing with a cylinder here, we're going to be dealing with pi times radius squared times the height for each cylinder, and then we'll multiply that by the number of cylinders. So in our case, that's going to be pi times, the bore is 0.85, and that means our radius is half of that, 0.425 inches. So pi times 0.425 squared times the height, that's our stroke, 1.500, just like finding engine displacement, times the number of cylinders. This was a 9-cylinder pump. Pi times 0.425 squared times 1.5 times 9. And it's a pretty small displacement, only a few cubic inches, and that's pretty typical, about 7.66 cubic inches. That's per revolution if you want to get real fussy about it. Each time it turns, it's going to pump 7.66 cubic inches. And now that we know that, we can use our formula. Our flow rate is going to be our displacement, 7.66 cubic inches, times the number of RPM, in this case that's 2400, divided by 231. And that turns out to be about 79.6. 79.6 what now? That's your flow rating in gallons per minute, 79.6 GPM, and we're good to go. Now, you can use this formula. Flow rate is displacement times RPM divided by 231 times for any kind of a hydraulic pump, and oftentimes the pump will specify on their tag on the side what the displacement per revolution is. We're only going to work with piston pumps because those are the ones that are easy to find the displacement. Other type of pumps like gear pumps or vane pumps are a little bit harder to find the displacement of, and we don't need to get that carried away. All right, well, if you can do that, you can do this. Take a minute, pause the video, and work this one and see if you can get the flow rating of this pump. It's a 5-cylinder with a bore and a piston that is 0.750 inches in diameter and a stroke of 0.750 inches at 1500 RPM. Go ahead and calculate the flow rate. Unpause when you're ready to see the solution. Okay, well, since your bore is 0.75, your radius must be half of that, or 0.375 inches. Therefore, our displacement is going to be pi r squared times the height times the number of cylinders. That's pi times 0.375, our radius squared, times our stroke of 0.75, since the bore and stroke were the same here, times 5 cylinders, and you should get about 1.66 cubic inches. That's the number we need for our formula. The flow rate is going to be 1.66 times 1500 divided by 231, and if you do that, you get about 10.8, and again, those are gallons per minute. About 10.8 gallons per minute is our flow rate. Good to go. Okay, the second, of course, key way that hydraulic pumps are rated is according to their pressure. And the pressure is going to be the maximum operating pressure that the pump can generate safely, given the limitations of its design and the amount of torque that can be put into the pump. And of course, the pressure doesn't determine how fast anything's going to move, which is a little counterintuitive. The pressure simply determines how much force the actuated member has. So if we're talking about hydraulic cylinder, which is about the simplest thing, the pressure determines how much force the cylinder is going to develop when it's extending or contracting. So now we've got a little bit of geometry to use. Let's determine the extending force and the speed, how fast it'll move, when a 4-inch cylinder with a 1-inch ram is powered by a pump that's rated at 5.6 gallons per minute at 2500 psi. Well, let's start with the force. We already know how to do that. Our wheel that we've used before says that force is equal to pressure times area. We know what the pressure of the hydraulic fluid is. That's 2500 psi. The question is, what is the area? So let's think about this for a minute. When this cylinder is being extended, the hydraulic fluid is being pushed into the back side or the primary side of the cylinder over here. It's trying to push that hydraulic cylinder out. So if you think about that, that means the hydraulic fluid is pushing on a circular piston whose diameter is 4 inches. The fact that there's a 1-inch ram doesn't affect the extending side because the ram is on the other side. That'll affect something we're going to do in just a minute. But when it's extending, it's just pushing against the whole cylinder. So, against the whole piston. So the area here will be pi times the radius, which must be 2 inches squared. And if you do that, you'll get an area of 12.57 inches squared. We like to keep 2 decimals on that for accuracy. It's going to push on an area of 12.57 inches squared. So to calculate our force, how much force will this thing deliver when it's extending? From our wheel, force is pressure times area. And so the amount of force that this thing is going to exert is the pressure, 2,500 psi. And that's exerted on an area of 12.57 square inches, which turns out to be 31,425 pounds of force. That's a force, remember, so that's going to be in pounds. So just about 16 tons of force. It's pretty phenomenal. And that takes care of the first part of our question, that is how much force it delivers. Now the second part of the question, how the speed, we haven't addressed that yet. So let's work with the speed for a minute. Here's the next formula of the day. The actuation speed, how fast a cylinder will move, that's called its actuation speed. That'll tell us in inches per second how fast the ram is going to move in and out on this cylinder. We need to know the flow rate of the pump and the piston area that we're using. So it's a pretty easy formula to use once we have the area, and we have that. So for our actuation speed, that's going to be equal to the flow rate of our pump, that's 5.6 gallons per minute, times 231, that's turning it from gallons into cubic inches, divided by the piston area it's using, that's 12.57, square inches times 60. So the thing I want you guys to notice here is that the backside of this piston, the volume does not matter. The length of the cylinder has no impact on any of this. The length of the cylinder does not impact the speed or the force. All that matters is the diameter of the cylinder. When you type these into your calculator, make sure you figure out what the top and bottom numbers are independently. So if you take 5.6 on the top times 231, that turns out to be 1293.6 divided by, on the bottom, 12.57 times 60 gives you a product of 754.2. And now if you divide that, you end up with 1.7. Now 1.7 what? Again, that's the speed. That's how fast the cylinder is going to move, and that is 1.7 inches per second. And I want to note here that that is the extending speed. And our force up here, that was the extending force. Okay, so we've answered those two questions. Now, we're going to take that a step further here. Now, when that cylinder goes to contract, the hydraulic fluid is going to be pushing in on the other side of the cylinder. It's going to be hydraulic fluid filling in around the ram, pushing that ram back into the cylinder. So now the hydraulic fluid doesn't get to push on that whole circle anymore. It has to push on this area around where the ram attaches. So we lose this hole in the middle. That donut shape is called an annulus. Now the size of the ram matters. It didn't matter in the problem we just did, but now it does. So let's find the area of this annulus. That's going to change our math a little bit here. So what we need to do is we need to take this whole piston, and then we're going to subtract out that hole in the middle. We already know what the whole piston was. The whole thing was 12.57. We did that in the previous example. That was the diameter of 4 inches. But now we need to subtract off the area of this place where the ram attaches. So if the diameter of the ram is 1 inch, the radius must be 1/2 inch, and the area will be pi times 0.5 squared, and that's 0.79 square inches. So 12.57 is the whole annulus, minus the hole in the middle, that's 0.79. And that turns out to be 11.78 square inches. that's the number we can use to figure out what the speed and force are when we're pushing the ram back into the cylinder or when we're contracting. So let's do that. So let's determine the contracting force and the speed. Same two questions we did it earlier, but this time we're dealing with the contracting force, so we're trying to push this thing back in. Now, philosophical question, is this thing going to have more or less force when it's pushing the cylinder back in? Well, it should be less, right? Because this hydraulic fluid doesn't have quite as much area to push against. It loses that hole in the middle, so there's not as much area to push against. That's going to reduce our force. So our contracting force, our wheel still says force is pressure times area. So our contracting force is going to be our pressure. That's no different, 2,500 psi. It's the same pump. Times our area. We just showed that that area, when we're pushing everything back in, we're going to be dealing with that area of 11.78 square inches. That's the result we got just a minute ago. So 2,500 psi times 11.78 square inches. Our contracting force is 29,450, and again that's a force, so those are pounds. Now, again, if we compare that to what we did just a minute ago, that is less. When we were extending, we had a little bit larger area, 12.57, and we had a force of 31,400 pounds. Now, because of the ram, we lose a little bit. We've only got 29,000. That's about 15 tons. Now our contracting speed, same idea. Let's do that. Our contracting speed is going to be our flow rate, same pump, 5.6 times 231, divided by our piston area. Again, that's only 11.78 when we're being drawn back in, times 60. So the top number, we already know what that top number is. That top number turns out to be 1293.6. We already did that in the previous case. The bottom number, 11.78 times 60, that turns out to be 706.8. That's a little different. Now when we divide that, what are you expecting? Are you expecting the speed to be faster or slower? Well, again, if you think about it, when the hydraulic fluid goes back in, the ram is taking up some of that volume. And so it doesn't take as much hydraulic fluid to fill the space because the ram occupies some of it. And that means that that ram is going to zip back in a little bit faster. And that turns out to be about 1.8 inches per second, which again is a little bit faster than we got when we were extending, and that was only 1.7 inches per second. So same math, but all done with a smaller area results in less force, but higher speed. Which is why I've always thought that log splitters should have a really, really big ram on them, because you don't need that much force when you're drawing the log splitter back. And it's kind of nice for when you're working to have that cylinder zip back in quickly so you can split the next log. At any rate, we're done. Let's move on. Okay, speaking of a log splitter, let's take a look at this one. This one is straight off of Northern Tools website. 37-ton log splitter, supposedly. A couple of things that matter. The first one is this is a 16-gallon per minute two-stage hydraulic pump. And it's a 2-inch ball hitch. No, I'm just kidding. That's not very important. We want to figure out, based on the size of the ram and the size of the cylinder, 5-inch cylinder, 2.5-inch ram, 16 gallons per minute at 3,500 psi. That's the pump that we're working with that's stuck on that little engine there. We want to find the extending speed, the extending force, the contracting speed, and the contracting force. Let's do that. Okay, let's think about this cylinder for a minute. It's got a 5-inch diameter cylinder with a 2.5-inch ram. When it's extending, that's pretty easy. The backside of this piston is just going to be a 5-inch circle. That means its radius is 2.5 inches, and therefore the area is going to be pi times 2.5 inches squared. And so the area when it's extending is 19.64. So we could do all the math on the extending side of this right now. Our extending speed, flow rate, 16 gallons per minute, times 231, divided by our area, 19.64 times 60. On the top, that gives you 3696. On the bottom, that gives you 1178.4 for an extending speed of 3.1 inches per second. Extending force, that's easy. We know 3,500 psi, so we can multiply that by our area. 3,500 psi times 19.64 square inches gives you 68,740. And again, those are pounds since it's a force. Now, just out of curiosity, if you divide that by 2,000 to turn it into tons, you end up with 34.37 tons. That is a little bit lower than the 37 tons that they claim here on their advertising. Why the difference? I don't know. We're not too far off, but something there doesn't quite line up. Okay, now let's talk about the contracting side. The contracting side is really going to be the same except for the annulus. When this hydraulic fluid goes in over here and fills up the right side of the cylinder in order to push the piston back down and to draw the ram in, it's going to be a smaller area. So we're going to lose that hole in the middle, and we need to find out what the area of that annulus or that donut is. So for starters, let's find out what the area of the hole is. That's going to be pi times our radius. Now, the ram is 2.5 inches. That means our radius is 1.25 inches, half of that, squared. 4.91 square inches. So that's how much we're going to lose because of where the ram attaches right there. And so the area of the annulus is going to be 19.64, the whole piston, minus the hole where the ram attaches. It's not really a hole, but the spot where the ram attaches. And you're going to end up with 14.73 square inches. Now, let's go ahead and do the same calculations, but we're going to use this smaller area. We should get a smaller contracting force, but a higher contracting speed. Our contracting speed is going to be, the top will be the same. It's still a 16 gallon per minute pump, right? 16 gallons per minute times 231 divided by, now we're going to use a smaller area, only 14.73 times 60. Top number, still going to be 3696. Bottom number, not going to be the same. Bottom number turns out to be 883.8. Then we'll divide 3696 on the top by 883.8, and that turns out to be about 4.2 inches per second. And as we expected, that's a little bit faster than when it was extending. That was only 3.1 inches per second. So our contracting force is, of course, pressure times area, and so that's going to be the same 3,500 psi we had from the same pump, 3,500 psi, times our smaller area of just 14.73 square inches, 51,555 pounds, which, again, no surprise, that's less force than when it was extending. We had almost 69,000 pounds. Now we're down to 51,000 pounds. So exactly what we said. It'll contract faster, but with less force. Okay, so let's hit the high points of that and summarize. Flow rate of a pump is determined in gallons per minute, and that determines how fast our cylinder or motor will actuate. And you can do that calculation. You can figure out what the flow rate is in gallons per minute if you know the displacement in cubic inches, like we've done before, times the RPM divided by 231. Common mistake is to miss the number of cylinders when you're finding displacement, so be careful of that. Then once you know your flow rate, you can figure out actuation speed. Actuation speed is your flow rate times 231 over your piston area times 60. That's in inches per second. There's your second formula. Make sure that one goes on your sheet. And your actuation speed, along with our force pressure area circle, will allow you to calculate extending forces and extending speeds, because all you need to do is find the area of the piston when it's extending. But when you go to work with the contracting side of the pump, when you're contracting, you're pushing the ram back in, and then because of the ram, you lose some of your pushing area, and so we have to subtract that circle in the middle where the ram attaches. And therefore, we can only push against this ring, or this annulus it's called. A common mistake here is to use the area of this inner circle when you're contracting. That's not true. You lose the area of this inner circle, and what you're left with is the donut. That is the area you can use when you go to find your contracting forces and actuation speed. So same formula, same force equals pressure times area, same actuation speed formula, but our piston area is smaller because we lose that hole. Don't hesitate to shoot me an email or a text if you have any trouble.